Light a match. Go ahead, do it in your mind. You strike it, the head flares up, and you get a little tongue of flame. It dances around for a while, eats its way down the wood, and then it goes out. The match is done. Finished. A small black stick with a curl of smoke. That is the entire story of every star that ever existed. Oh, sure, the details are fancier, the temperatures are absurd. The pressures would crush anything you have ever touched into something you would not recognize. The timescales stretch so far that human civilization is not even a blink. But the basic plot: a star is a match. It lights, it burns, it goes out. And the question I want to chase today is not just how that happens, because that part we can manage pretty well. The real question, the one that should make you a little uneasy, is what is left when the last match goes out. When every star in the universe has burned through everything it has got, what then? Let us start where all good physics starts, with something embarrassingly simple. Why does a match burn? You have got a stick of wood with some chemicals on the tip. You drag it across a rough surface, you add a little friction, a little heat, and that heat is enough to kick off a chemical reaction. The chemicals on the match head break apart and recombine with oxygen from the air, and that recombination releases energy, more heat, which lights the wood, which releases more heat, and so it goes until the fuel runs out. The whole thing is a chain reaction driven by one basic fact: the products of the burning have less energy locked up inside them than the original fuel did. The difference comes out as heat and light. Simple, beautiful, and exactly what a star does. Except instead of wood and oxygen, you have got hydrogen. And instead of a chemical reaction, you have got a nuclear one. Let me be clear about the difference, because it matters enormously. A chemical reaction rearranges the electrons around atoms. It changes the partnerships between atoms, but leaves the atoms themselves intact. You burn wood, and the carbon and hydrogen atoms in the wood combine with oxygen atoms in the air. The atoms survive, they just find new partners. A nuclear reaction does something much more dramatic. It changes the atoms themselves. It reaches inside the nucleus, the tiny dense core of the atom, where almost all the mass lives, and rearranges the protons and neutrons. It takes one element and transmutes it into another. That is a much bigger deal. The energy locked in nuclear bonds is roughly 1,000,000 times greater than the energy in chemical bonds, which is why a nuclear power plant can run an entire city on a few truckloads of fuel, while a coal plant needs entire trainloads every week. Deep in the core of a star, the pressure is so enormous and the temperature so ferocious. We are talking about 15 million degrees at the center of the sun, that hydrogen nuclei, which are just single protons, get slammed together hard enough to overcome their electrical repulsion and stick. Protons are positively charged, and positive charges repel each other. Under normal conditions, two protons will never touch. They shove each other away. But at 15 million degrees, the protons are moving so fast that they can barrel through that electrical barrier and get close enough for the strong nuclear force, the force that holds nuclei together, to grab them and bind them. They fuse. 4 hydrogen nuclei combine through a few intermediate steps involving deuterium and helium-3 into one helium nucleus. And here is the kicker. If you weigh the helium at the end, it weighs slightly less than the 4 hydrogen nuclei you started with. A tiny bit of mass has vanished. About 0.7% of the original mass, to be precise. Less than 1%. That does not sound like much. And if you were doing a chemistry experiment on a benchtop and you lost 0.7% of your mass, you would barely notice. It would not heat your coffee. But a star is not a benchtop experiment. It is a ball of gas so large that 1.3 million Earths could fit inside it. We are talking about an object that contains 2 times 10 to the power of 30 kilograms of material. 2,000 billion kilograms. When you take 0.7% of that and convert it into energy using Einstein's formula E equals mc squared, where c is the speed of light, 186,000 miles every second, you get a number that should make you sit down. Every second our sun converts about 4 million tons of its own mass into pure energy. 4 million tons gone every single second, turned into photons and neutrinos and kinetic energy, blasting outward in every direction. And the sun has been doing this for roughly 4.5 billion years. It has lost about 100 Earth masses worth of material in that time, and it has barely noticed. That is how much hydrogen it started with. So there is the first layer. A star is a nuclear furnace that converts mass into energy by fusing light elements into heavier ones. Simple enough. Light the match, watch it burn. But already, something interesting is hiding in that picture. Something that makes a star fundamentally different from a match. A match burns from the outside in. The flame sits on the surface, eating inward. A star burns from the inside out. The nuclear reactions happen in the core, where the pressure and temperature are highest. Only the innermost 10% or so of the sun's mass is actually hot enough and dense enough for fusion to occur. The rest of the star is just sitting there, a gigantic insulating blanket being held up, and that word held up is where the story takes a turn. A star is not just burning, it is fighting. Every moment of its life, from the instant it first ignites to the moment its fuel runs out, a star is locked in a war between two forces, and the outcome of that war determines absolutely everything about how that star lives and how it dies. On one side you have gravity. Gravity wants to crush the star, pull every atom toward the center, collapse the whole thing into the smallest, densest configuration possible. Gravity is patient. It has no schedule. It does not get tired. It never takes a day off. It just pulls, steadily, relentlessly, every second of every year for billions of years. On the other side you have pressure. The nuclear reactions in the core generate colossal amounts of heat. That heat makes the gas want to expand. You have thermal pressure pushing outward. You have radiation pressure from all those photons bouncing around trying to get out, and together they shove against gravity, holding the star up like a balloon inflated from within. For most of a star's life, these two forces are in a precise, delicate balance. Gravity pulls in, pressure pushes out, and the star just sits there, enormous and stable, shining steadily. This balance has a name in physics: hydrostatic equilibrium. Fancy words for a tug of war that neither side is winning. And the star appears to be perfectly content, stable, unchanging, over human timescales. But here is the thing that nobody tells you when they first explain how stars work. This equilibrium is not free. The star has to pay for it, continuously. Every second of that balance costs fuel. The star has to keep burning hydrogen, keep running the fusion furnace, to keep producing the outward pressure that prevents gravity from winning. If the fusion stops even briefly, gravity starts to squeeze, and things go bad very quickly. Think of it like treading water in the middle of the ocean. You can keep your head above the surface, sure, but only as long as your legs keep kicking. You can tread water for hours if you are strong enough. But eventually your muscles run out of glycogen, your legs cramp, your arms get heavy, and the ocean does not care, does not give you credit for the hours you already spent kicking. It does not owe you anything for past effort. Stop kicking, and down you go. That is exactly the deal a star is made with gravity. Keep burning or collapse. Those are your two options. So, a star is not just shining beautifully in the sky. It is spending its hydrogen, converting it into helium ash, and paying gravity's tax every second of every day. This is the first way time kills a star. Not with a dramatic blow, not with some cosmic catastrophe. Just a slow, quiet, unrelenting invoice. You owe 4 million tons per second. Please pay at the door. Let us add another layer now. What happens when the hydrogen in the core runs out? The depth proof, because it will run out. Make no mistake about that. In a star like our Sun, the core has enough hydrogen to last roughly 10 billion years. We are about halfway through, so we have got some time. But 5 billion years from now, give or take, the Sun's core will be mostly helium. The hydrogen fuel that has been keeping the lights on will be spent. At that point, the fusion reactions in the core slow down and eventually stop. Less fusion means less heat. Less heat means less pressure pushing outward. And what has been waiting patiently on the other side of that tug of war this entire time? Gravity. Gravity starts winning. The core begins to contract. But something genuinely remarkable happens. As the core contracts, it gets hotter, not cooler, hotter. That might seem backwards at first, but it makes perfect physical sense. When you compress a gas, the particles get closer together. They bounce off each other more often and more violently, and the temperature rises. You have felt this if you have ever pumped up a bicycle tire and noticed the pump getting warm in your hand. Same principle, unimaginably larger scale. The core contracts under gravity's squeeze and the temperature soars. From 15 million degrees it climbs to 100 million degrees. And at that temperature, a new set of reactions becomes possible. The helium that has been accumulating, As the waste product of hydrogen burning, the ash of the first fire suddenly becomes fuel for a second fire. Helium nuclei start fusing together. 3 helium nuclei combine to create a carbon nucleus in a process called the triple alpha reaction. The star has found a second match. But while all this drama is happening in the core, something spectacular happens to the outside of the star. The energy pouring out of the newly ignited helium furnace, plus the hydrogen still burning in a shell around the core, floods outward and pushes the star's outer layers to enormous distances. The star swells. In the case of our Sun, 5 billion years from now, it will expand until its outer edge reaches roughly the orbit of Mars. Its surface will be cooler than it is today, glowing a deep red instead of white-yellow, but it will be gigantic. A red giant. If you could stand on what is left of the Earth, the Sun would fill most of your sky. A bloated, dying furnace, puffing up because its core is desperately trying to keep the lights on with a less efficient fuel. This is not a graceful aging. This is a star losing control of its own structure. The careful balance between gravity and pressure that lasted for billions of years is breaking down. The core is contracting and heating while the envelope is expanding and cooling. The star is tearing itself apart from the inside slowly over millions of years. This sounds like a reprieve, does it not? The star has adapted, found a way to keep going. But watch closely, because the star is not solving its problem. It is postponing it. And the terms of the postponement are terrible. Helium burning produces energy, yes. But it produces less energy per reaction than hydrogen burning did. And it burns faster. Much faster. A star like the Sun might burn hydrogen in its core for 10 billion years. The helium burning phase lasts only about 100 million years. 1% of the hydrogen burning lifetime. The star is suddenly spending its reserves at a dramatically higher rate, getting less return on each reaction. Like a person who runs out of their savings account and starts living on credit cards. Sure, you can keep the lights on for a while longer, but the interest is accumulating and you are heading for a wall. Meanwhile, the carbon produced by helium fusion is heavier than helium. It sinks to the center of the core, so now the star has developed a layered structure, a core of carbon surrounded by a shell where helium is still fusing, surrounded by a larger shell where hydrogen is still fusing on the outskirts, an onion of elements. Each layer is the ash of the reaction happening in the layer above it. Now for a star like the Sun, this is roughly the end of the line. The Sun is not massive enough to compress its carbon core to the temperatures needed for the next stage of fusion. When the helium is exhausted, the core simply contracts, heats up some more, but never quite gets hot enough to ignite carbon. The outer layers puff off into space, forming what we call a planetary nebula, and the naked core is left behind as a white dwarf. We will come back to white dwarfs later. They have a fascinating story of their own. But for stars that are much more massive than the Sun, 8 times, 10 times, 20 times its mass, the game continues. Carbon ignites, it fuses into neon and oxygen. Then neon ignites and fuses into more oxygen and magnesium. Then oxygen ignites and fuses into silicon and sulfur. Then silicon ignites and fuses into iron. Each stage is shorter than the last, dramatically shorter. And I want you to feel the acceleration here because it is stunning. A massive star might burn hydrogen in its core for 10 million years. That is its main sequence, lifetime, the long, stable, productive part of its life. Then it burns helium for about 1 million years, already a factor of 10 shorter. Then carbon burns for roughly 1,000 years, another factor of 1,000 shorter. Neon burning lasts about 1 year, oxygen burning a few months, and silicon, the very last stage of nuclear fusion, burns for approximately 1 day. One day, a star that spent 10 million years casually fusing hydrogen will tear through its entire silicon reserve in about 24 hours. The pace of death accelerates exponentially. Time is not killing this star at a constant rate. It is stampeding, and every one of these fusion stages produces less net energy than the one before. The energy yield drops, the duration shrinks, the star is working harder and harder for less and less return, running faster and faster on a treadmill that keeps getting steeper. So why does it keep going? What choice does it have? The alternative to burning is collapsing, and each time gravity squeezes a little harder on the core, the temperature rises just enough to ignite whatever fuel is available next. The star does not choose to burn silicon, it is forced to, by the relentless inward pressure of its own weight. Each new fuel is a smaller and more desperate fire, lit by gravity's squeeze. Now we arrive at the crisis, the moment that changes everything. Iron. When silicon fuses in the core of a massive star, the product is iron. Iron 56 to be specific, the most common isotope, and iron is special. Iron is the end of the road, the absolute dead end. Every fusion reaction we have discussed up to this point, hydrogen to helium, helium to carbon, carbon to oxygen, all the way to silicon to iron, every single one of them releases energy. You combine lighter nuclei into a heavier one, the product has less total mass than the ingredients, and the missing mass comes out as energy. That is the fuel. That is what has been keeping the star alive this entire time. But iron sits at the very bottom of what physicists call the binding energy curve. The nucleons in an iron nucleus, the protons and neutrons, are bound together more tightly than in any other element. This means that if you try to fuse iron into something heavier, the product does not weigh less than the ingredients. It weighs more. You have to put energy in instead of getting energy out. Fusing iron does not release energy, it absorbs it, which means a core full of iron is a core that cannot generate any more pressure from fusion. The furnace has produced its own poison. The last fuel has created the one element that cannot be burned. The fire goes out, not gradually, not like a candle guttering in a draft. The iron core accumulates in the center of the star over the course of that final day of silicon burning, growing heavier and denser. When it reaches about 1.4 times the mass of the Sun, a threshold called the Chandrasekhar limit, electron degeneracy pressure, which is the last thing holding the core up, is no longer sufficient. The core has exceeded the maximum mass that electrons can support, and gravity, which has been waiting patiently for exactly this moment, waiting since the very first hydrogen atoms fell together to form the star, all those millions of years ago, gravity finally, irrevocably wins. What happens next depends on the mass of the star, and it happens with a speed that is genuinely terrifying. The iron core, no longer supported by any outward pressure from fusion, begins to collapse, and it does not collapse gently. In a star that is 10 or 15 or 20 times the mass of the Sun, the core collapse takes less than 1 second. In that fraction of a second, the core goes from being roughly the size of the Earth, several thousand miles across, to being a ball roughly 12 miles in diameter. 12 miles, the distance you might drive to go get groceries. The matter has been compressed so violently that protons and electrons have been smashed together to form neutrons. Essentially, the entire core becomes one gigantic atomic nucleus. The density is beyond any meaningful comparison. A single teaspoon of this material, if you could somehow scoop it out and bring it back to Earth, would weigh about 1 billion tons. 1 teaspoon, 1 billion tons. This is a neutron star. The outer layers of the star, which were still fusing merrily in their nested shells, hydrogen on the outside, helium below that, carbon, oxygen, all the way down, these layers suddenly have nothing underneath them. The floor they were resting on has just collapsed out from under them at 1/4 of the speed of light. They fall inward, accelerating, and then they slam into the surface of the neutron star, which is so incompressibly dense that it acts like a solid wall. They bounce. I want you to appreciate how remarkable that word is. Bounce. This is not a tennis ball hitting a wall. This is several solar masses of gas falling inward at 70,000 kilometers per second, hitting a surface harder than anything else in the known universe. The bounce creates a shock wave that for a moment stalls. The infalling material piles up behind it. For a few hundred milliseconds, it looks like the explosion might fail. The shock wave might stall out and fall back. The star would just quietly collapse into a black hole without any fanfare. In some cases, that probably happens. But in many cases, the flood of neutrinos, 100 billion of them released in about 10 seconds, deposits just enough energy in the stalling shock wave to revive it and push it outward. That bounce, combined with that titanic flood of neutrinos, blows the outer layers of the star apart in all directions. A supernova, specifically a core collapse supernova, also called a Type II supernova. For a few weeks, this single dying star outshines an entire galaxy. One star brighter than 100 billion stars combined. All that energy, all that brilliance, is the final scream of a furnace that ran out of fuel. The match is going out, and it goes out with the most violent explosion in the known universe. And in those final violent seconds, something happens that is almost miraculous. Remember how I said fusing elements heavier than iron costs energy instead of producing it? A star cannot do it during its normal life, because there is no profit in it. But a supernova does not care about profit. A supernova has so much excess energy slamming around, so many free neutrons flooding through the expanding debris, that heavier elements get forged anyway. Gold, platinum, uranium, iodine, all the elements heavier than iron on the periodic table, the ones you cannot make by steady fusion inside a star, those get hammered together in the chaos of the explosion itself. It takes a dying star to make them. The gold in a wedding ring was created in about 10 seconds during a supernova that happened long before our solar system existed. That is where it comes from. There is no other way to make it. So the supernova is not just a death. It is also a delivery. It scatters all those newly minted elements, along with the carbon and oxygen and silicon that the star cooked up during its lifetime, outward into space at thousands of miles per second. Those elements mix into the surrounding gas. Eventually, that enriched gas gets pulled together by gravity into new clouds, new stars, new planets. Planets with iron cores and silicon crusts and oceans of water and traces of gold and iodine and all the rest. Everything the next generation of stars and planets needs was delivered by the death of the previous generation. You cannot separate stellar death from stellar creation. They are the same process. Every end seeds a beginning, at least for a while. But let us pull back now. Let us stop thinking about one star and start thinking about all of them. Our galaxy, the Milky Way, contains somewhere between 200 billion and 400 billion stars. The observable universe contains on the order of 2 trillion galaxies. That is a lot of matches, an absurd number of matches. And every single one of them is burning down. Every star you see in the night sky, every star you cannot see, every star in every galaxy stretching out to the very edge of what light has had time to reach since the Big Bang, all of them are spending their fuel. All of them are slowly, inevitably losing the fight against gravity. Some burn fast. The blue supergiants, the really massive ones, 30 or 50 times the mass of the sun, might last only a few million years. They burn furious and bright and die young. Others, the little red dwarfs, stars much smaller than our sun, burn so slowly and so efficiently that they can last for trillions of years. Not billions, trillions, far, far longer than the current age of the universe. The universe is roughly 13.8 billion years old, and there are stars that will keep quietly burning for 10 trillion years or more. Patient little candles, barely brighter than a nightlight. But even they are burning, even they are spending. The match is long, impossibly long compared to ours, but it is still a match. It still has an end. So what happens when all the matches go out? This is where the story gets genuinely strange and I think beautiful in a very cold, very quiet sort of way. Imagine the far future, not a billion years from now. Not even a trillion. Let us go out to the point where the last red dwarf, that patient little candle that outlasted everything else, has finally sputtered and dimmed and gone dark. We are talking perhaps 100 trillion years from now. 100 trillion. The current age of the universe is a rounding error compared to this time scale. The universe is dark. There are no more fires, no more fusion anywhere. The raw material of stars, the hydrogen gas that filled the young universe, has either been locked up inside dead stellar remnants, processed through fusion into heavier elements, or scattered so thin across the ever-expanding volume of space that it can never again collect into clouds dense enough to form new stars. The era of starlight is over. What is left? More than you might think, actually. It is not as though matter has disappeared. There are still enormous numbers of objects out there. Rogue planets, ejected from their star systems by gravitational encounters, drifting alone through the dark. Brown dwarfs, objects that were almost massive enough to ignite fusion but never quite made it, slowly cooling from whatever feeble warmth they once had. Asteroids, comets, dust, and then the 3 main categories of stellar corpses, each with its own strange physics. Occasionally, very occasionally, 2 brown dwarfs might collide and merge. If their combined mass crosses the threshold, fusion could briefly ignite, a new star born from the merger of 2 failed stars, flickering to life in a universe that has otherwise gone dark. These events would be extraordinarily rare, separated by vast stretches of empty time, a single candle lit in a warehouse the size of a continent, burning for a few billion years, then going out. But they could happen. The universe's last sparks. Eventually, though, even these become impossible. The objects drift too far apart. The probability of collision drops to effectively 0. And what remains, truly and finally, falls into 3 categories. First, white dwarfs. These are the remains of stars like our sun, and smaller, Stars that were not massive enough to collapse into neutron stars or blow themselves apart as supernovae. Instead, they shed their outer layers gently over thousands of years, puffing them off into space as beautiful glowing shells of gas, what astronomers call planetary nebulae. What remains behind is the core, a dense ball of carbon and oxygen, sometimes with a thin skin of helium or hydrogen, roughly the size of the Earth, but with the mass of the entire Sun crammed inside. No fusion. The nuclear fires are permanently out. What keeps the white dwarf from collapsing further is not heat, but a quantum mechanical effect, the fact that electrons obey the Pauli exclusion principle and resist being compressed into the same state. Electron degeneracy pressure. The corpse is held up not by energy, but by a law of quantum mechanics. With no energy source, the white dwarf just radiates its leftover heat into space. Slowly, it glows white at first, then yellow, then orange, then red, then dimmer and dimmer, cooling over billions of years, then trillions. Eventually, after an almost unimaginable stretch of time, the white dwarf becomes a black dwarf, a cold, dark, crystallized lump of carbon drifting through empty space, giving off no light, no heat, nothing detectable. As far as we know, no black dwarfs exist yet anywhere in the universe. It has not been long enough. The universe is simply too young, but they will come. Second, neutron stars. The crushed cores of massive stars that went supernova. Born spinning rapidly, some of them hundreds of times per second, with magnetic fields trillions of times stronger than Earth's. They shoot beams of radiation from their magnetic poles, sweeping through space like lighthouse beacons. We call the ones we can detect pulsars. But every rotation costs energy. The spinning slows, the beams weaken. Over millions and then billions of years, the neutron star winds down, cools off, and goes quiet. Just a dense, dark object, 12 miles across, with the mass of 1 or 2 suns drifting silently through the void. Third, black holes. When the most massive stars die, their cores do not even stop at neutron star density. The gravity is too strong. The collapse continues past every limit, past every possible source of outward pressure, down to a singularity, a point of theoretically infinite density wrapped inside an event horizon, a boundary in space from which nothing, not light, not information, not anything can escape. Black holes are the ultimate gravitational victory. Gravity won so thoroughly that it swallowed the star entirely and closed the door behind it. So picture this far future universe. Dark, scattered with white dwarf corpses slowly cooling toward absolute zero, neutron star cinders spinning down to silence, and black holes, invisible and patient, scattered through stupendous volumes of cold, expanding space. No light, no warmth, no fire. Is that the end? Is the story finished? Almost, but not quite, because even the corpses have stories left to tell, if you are willing to follow the clock far enough. Let us go deeper, much, much deeper into the future. On timescales that make the current age of the universe look like the opening flicker of a very long film, things continue to happen. Slowly, agonizingly slowly, but they happen. The galaxies dissolve. Right now, stars in a galaxy orbit a common center, held together by their mutual gravitational attraction. But every so often, 2 stars pass close enough for one to give the other a gravitational kick. Over enormously long stretches of time, these random encounters eject most of the stars from the galaxy altogether, one by one, flinging them out into intergalactic space. The galaxy evaporates like a puddle in weak afternoon sunlight. The process takes something like 10 to the power of 19 or 20 years. The remaining stars and stellar remnants that do not get ejected spiral inward and fall into the supermassive black hole, sitting at the center of the galaxy, feeding it and making it grow. Next, something that sounds almost impossible. Protons themselves may decay. The proton is one of the most stable particles we know. No one has ever observed a proton falling apart. We have looked very carefully in enormous underground tanks of ultra-pure water surrounded by sensitive detectors, and we have never seen it happen. But several serious theoretical frameworks in physics, in particular the grand unified theories that try to merge the strong nuclear force with the electroweak force, predict that protons are not truly eternal. They might have a half-life, an almost inconceivably long half-life, something on the order of 10 to the power of 36 to 10 to the power of 41 years. A 1 followed by 40 zeros, a number so vast that it has no analogy in human experience. It is not like anything you have ever counted or measured or imagined. But the universe, if it lasts forever, has unlimited time. And if protons do decay, then eventually, atom by atom, every white dwarf, every neutron star, every piece of ordinary matter in the universe will crumble. Think of a marble statue left out in the rain. Each year a few molecules dissolve. You cannot see the change. Come back in 100 years, and you might notice the nose is slightly softer, the fingers a bit rounder. Come back in 1,000,000 years, and the statue is an unrecognizable lump. Come back in 10 million years, and there is nothing there at all. Proton decay does the same thing to matter, but on a time scale that makes the erosion of marble look like an explosion. The carbon lattice of the black dwarfs will disintegrate. Crystal by crystal, atom by atom, proton by proton, the neutrons in the neutron stars will break down, their constituent quarks falling apart into lighter particles. Everything solid, everything we think of as permanent matter, dissolves into a thin haze of electrons, positrons, neutrinos, and photons. The corpses themselves rot away. And the black holes? Surely the black holes from which nothing can escape are at least permanent. No. This is one of the most astonishing results in all of 20th century physics. In 1974, Stephen Hawking demonstrated theoretically that black holes radiate. They are not perfectly black. Through a subtle process involving quantum mechanical fluctuations near the event horizon, the boundary of the black hole, pairs of virtual particles can be separated. One falls in, the other escapes as real radiation. The black hole loses a tiny amount of mass with each emitted particle. This is called Hawking radiation. For any black hole that exists today, this effect is phenomenally weak. A black hole with the mass of the Sun would have a Hawking temperature far, far below the current temperature of the cosmic microwave background radiation, which means it is actually absorbing more energy from its environment than it radiates. It is gaining mass, not losing it. But in the deep future, after the cosmic background radiation has been redshifted to essentially zero by the expansion of space, the black holes will finally be warmer than their surroundings, and they will begin to evaporate, slowly, particle by particle, photon by photon. How slowly? A black hole with the mass of the Sun would take roughly 10 to the power of 67 years to evaporate completely. The supermassive black holes at the centers of former galaxies with masses of billions of suns would take on the order of 10 to the power of 100 years. That is a 1 followed by 100 zeros. I cannot make you feel that number. No analogy will do it justice. It is not 1,000,000,000 years. It is not 1,000,000,000,000 years. It is so much vaster than any timescale I have mentioned so far that those timescales round to zero by comparison. But it is not infinity. It is a finite number. And when that time has elapsed, the black hole emits its last burst of particles, and it is gone. After the last black hole evaporates, what remains? A universe of photons, leptons, and other light particles, each drifting apart as space continues its expansion. The temperature is asymptotically approaching but never quite reaching absolute zero. The density is approaching but never quite reaching true vacuum. Every particle moves farther from every other particle. Interactions become rarer and rarer. The time between events stretches and stretches. Eventually nothing happens. Not just for a while, effectively forever. No structures form, no reactions occur, no information is processed, no change takes place. This is what physicists call the heat death of the universe. And the name is misleading because it is not death by heat. It is death by the absence of useful heat. Death by the spreading out of energy until it is everywhere and nowhere, equally distributed, utterly uniform. No hot spots, no cold spots, no gradients, no flows. The entropy of the universe has reached its maximum. Everything that can happen has happened. The story is over. And this is the deepest layer, the thing that has been lurking underneath every other layer since I lit that match at the very beginning. When the match burns, the products, the ash and the smoke and the warm air, have less useful, concentrated energy than the match head and the wood did before you struck it. Energy was not destroyed. The total amount of energy is the same as it was before, but it has been spread out, diluted, degraded from a form that could do something, a compact chemical fuel, into a form that cannot disperse warmth in the air. The match increased the entropy of the universe. Every process we have talked about today does exactly the same thing. Hydrogen fusion spreads energy outward as starlight. Helium fusion does it less efficiently, faster. Core collapse and supernova explosions scatter heavy elements and radiation across light years of space. White dwarfs radiate their remaining heat into the void. Hawking radiation bleeds energy away from black holes into the cold expanse. Every single one of these processes moves energy from a concentrated useful form to a diluted useless form. That is the second law of thermodynamics. Entropy increases. The total disorder of a closed system never decreases. Useful energy degrades into waste heat. Think about a pot of boiling water on a stove. The stove concentrates energy in the pot. The water is hot. The kitchen air is cool. And that difference is useful. You can cook with it. But turn the stove off, and the heat from the water gradually spreads into the air, into the walls, into the floor. After enough time, everything in the kitchen is the same temperature. The energy is all still there, every bit of it, but it is useless now. You cannot cook with a room that is uniformly 2 degrees warmer than it was before. The energy has been democratized, spread out equally. An equal distribution of energy is the same as no useful energy at all. The universe is that kitchen. And the stove got turned off about 13.8 billion years ago. The second law is not a wall you suddenly hit at the end of the universe. It is a slope you have been sliding down since the beginning. Everything, from the moment the Big Bang happened, has been rolling downhill. Stars, planets, chemistry, life, thought, civilization, all of it is a consequence of the downhill roll. All of it is powered by the flow from low entropy to high entropy, from concentration to dilution, from order toward disorder. A star is just a brief, magnificent interruption in that slide. For a few billion years, gravity collects matter into a dense clump, fusion lights up, and the star shines. But it shines precisely by converting concentrated nuclear energy into dilute radiation. It does not create energy, it degrades it. The star is a machine for turning useful energy into less useful energy, and it produces light and warmth and the conditions for life as a side effect. You and I exist because of that side effect. Everything interesting that has ever happened, every chemical reaction that built a molecule, every cell that divided, every brain that formed a thought, every word that was spoken, all of it is powered by the flow of energy downhill, from the hot core of a star through space to the cold void. We surf the gradient. When the gradient flattens out, when everything is the same temperature, the surfing is done. So what should you take from all this? I think the wrong reaction is despair. People hear a story like this and they think, well, if everything ends in an empty, cold, dark, dead universe, then what is the point of anything? But that conclusion misses the most important part of the story. Look at what happens on the way down. Look at the extraordinary creativity of matter and energy when they are out of equilibrium, when there is a gradient to exploit. Stars take hydrogen and build the periodic table out of it, element by element, right up to iron. Supernovae add the rest, forging gold and uranium and every heavy element in those violent final seconds. Those elements get scattered into space, mixed into clouds of gas that collapse again to form new stars and new planets, planets made of silicon and iron and carbon and oxygen, elements that did not exist when the universe was young. On at least one of those planets, the chemistry got complicated enough to start copying itself. Molecules that could reproduce. Molecules that could vary and be selected. Life. 4 billion years of evolution produced organisms that can look up at the stars and wonder how they work. That is you, sitting right here, made of atoms that were assembled inside a star that exploded before our sun even existed. All of that, every bit of it, is powered by the temporary energy gradient between a hot star and cold surrounding space. It is the second law of thermodynamics in action, not as a death sentence, but as the engine of everything worth looking at. The match is burning down. Certainly, every match in the universe is burning down. But look at what the light makes possible while it lasts. And consider the timing. Right now, in this very brief window of cosmic history, we live in a universe that is ablaze with stars. Hundreds of billions of galaxies, each containing hundreds of billions of stars, all shining at once. We are living in the bright period, the fireworks display. In the deepest sense of the word, this is the interesting part. The part where things happen, the part where chemistry has fuel to work with and evolution has energy to exploit and minds have something to wonder about. 100 trillion years from now, when the last star is burned out and the universe is nothing but cooling corpses and slowly evaporating black holes, there will be nothing left to wonder and nothing left to wonder with. We happen to exist in the brief, luminous interval between ignition and ash. One more thought, because it would bother me to leave this out. The whole story I have told you depends on one enormous unexplained fact. The universe started with low entropy. The Big Bang produced a state that was extremely hot, extremely dense, extremely uniform in some ways, but with just enough tiny irregularities for gravity to amplify. That initial state had an enormous amount of room to spread out, an enormous capacity for entropy to increase. If the universe had started at maximum entropy, with everything already spread out, nothing would ever have happened. No stars, no light, no chemistry, no life, nothing. Just eternal, featureless equilibrium. So the real mystery, the one sitting underneath everything I have told you, is not why the universe will eventually die. That part follows logically from the second law. The mystery is why it was ever alive in the first place. Why did the universe start in a low entropy state? What wound the spring? Some physicists think the answer lies in the specific geometry of the early universe, in the way gravity behaves at cosmological scales, making the uniform early state actually a very low entropy configuration when you account for gravitational degrees of freedom. Some think it might require entirely new physics to explain. Some think the question itself may not be well posed. I do not have the answer. Nobody does, but I believe it is the right question, and I find it extraordinary that we can even formulate it. So let me leave you with one final image. You are sitting here, right now. Your body is made of atoms that were fused in the cores of stars that lived and died before the sun was born. The carbon in your muscles, the calcium in your bones, the iron in your blood, all of it was manufactured inside a stellar furnace and distributed by a supernova explosion. You are literally stardust that has organized itself into something that can think about stardust. And the energy that powers your thoughts at this very moment traces backward through the food you ate, through the sunlight that grew that food, through the nuclear reactions in the core of the sun, through the gravitational collapse of the gas cloud that formed the sun 4.5 billion years ago, all the way back to the low entropy initial conditions of the Big Bang itself. You are running on the original spring. The matches are all burning down. Every one of them. And nothing we know of in physics can stop that. But between the lighting and the going out, between the low entropy beginning and the high entropy end, there is room for an almost incomprehensible amount of interesting things to happen. Galaxies, stars, planets, oceans, forests, cities, conversations, ideas. We are one of those things. I do not find that depressing. I find it the most astonishing fact I know. If you had to explain to a child using nothing but objects in your kitchen why the stars cannot burn forever, what would you reach for? What would you light?